This is Unit 2, Exponential Functions. This is Day 5, Logarithms. Now, logarithms, they are the inverse operation to an exponential expression. And what I mean by that, let's say you have b to the y equals x. That's an exponential expression. Y is your exponent. If you wanted to solve the equation for y, you would have to use a logarithm. The logarithm would have a base of b and would be of x. So it would be y equals log with a base of b of x. The b is a subscript. It's written on the line. If you're on lined and ruled paper, it would be on the line a little bit below. That would be fine. It's subscript. And x is back on the line. You can see some written right here that log base 3 of 27 is equal to y. 3 to the y is equal to 27. That would actually be 3 to the third power. We would be able to get a 3 from typing this into our calculator, and I'll show you more about how to use a calculator with this thing in a little bit. Now, some people actually go back and forth from exponential form to logarithmic form using the previous screen where you have all the arrows and just remembering what happens. I teach it slightly different than that. I teach it as an operation. So like if I'm wanting to write this in exponential form, right now it's in logarithmic form, first thing I do is identify the base. I know the base is 3. And both this, log base 3 of 9, and the 2, those are both exponents of 3. So I'm going to write 3 as my base, and I'll just write the log base 3 of 9 as an exponent, and the 2 as an exponent. Now what happens over here on the left is the log base 3 and the base of 3 cancel to where you're left with simply a 9 equals 3 squared. And sure enough, that's true. 3 squared is equal to 9. Now going into logarithmic form from exponential, I'll take a logarithm on both sides. The logs will have a base of 27 because that's the base of my exponential. Log base 27, log base 27. And it will be of what's on each side. So 27 to the third and of 3. I usually write parentheses in when I'm writing logarithmic form. That's just how the calculator does it, so I've gotten used to doing that. Over here on the left, the base of 27 of the logarithm and the base of 27 of the exponential cancel. And you're left with simply the 1/3 equals logarithm with a base of 27 of 3. And now I've got my answer in logarithmic form. So I know 1/3 is the exponent that will raise 27 to the third power. Really useful for solving problems whenever it doesn't come out to a rational answer. Now to evaluate these. If you're evaluating a logarithm, what you would have to do is maybe set it equal to x. This is doing it by hand. In the next screen, I'm going to show you exactly how to do it with a calculator. So you'll set it equal to, let's say, x. And what you'll do now is actually figure out what x would need to be. I see my base is 3, so I'm going to put my base as 3 for both sides. And the 3's cancel over there, and you're left with 243 equals 3 to the x. And now this is going back to the previous day's lesson, where you'd figure out what power would raise 3 to 240. Did some work on the calculator, figured out that it was 3 to the 5th power would be 243. So x would equal 5, 5 being the answer. Now, I would never expect you to go through all of that to solve this problem. Let me show you how to do it on a calculator. Okay, what I'm going to expect you to use is your calculator. Let's save some time and just let it do the work. To do logarithm base 3 of 243, you will do alpha f2. Brings up a pretty long menu here. On mine, yours might be shorter. It's the 5th option right here. Again, to get this menu, I did alpha F2, which is the window key. It'll be the 5th option is what we're looking for. So I'm going to arrow down to that and hit enter on alpha F2. Now it brings up the expression. All we have to do is type it in, 3 logarithm base 3 of 243. And when I hit enter, it gives me 5. I would have my answer for part A. A lot easier than having to do it by hand. Also, sometimes these don't end up being rational answers, so the calculator will give you an approximation, which is really beneficial. Going on to part B, You could do that very same process I just did to evaluate part A, but here's your tip. This is a base of 10, which is a really, really common base to see for logarithms. When you see a base of 10, that happens a lot because scientific notation is written using bases of 10. Now, to do a base of 10, you don't have to go through the menu screen. You can actually use the logarithm key. If I were to press that, you will see that it doesn't write a base in for logarithm. When it is base 10, it is assumed, if you don't write it in the logarithm, it's assumed that it's a base 10. So I'll just type in log of 1,000. And when I hit enter, I get 3. That's because 10 to the third power is 1,000. So just to emphasize something really quick, if ever you saw this problem given to you, and it didn't say a base, you assume that base is 10. So keep that in mind. That's really common to see. Hence, it's called the common logarithm. All right, going to go ahead and graph this function and its inverse. For the function at the beginning, I'm going to do so in green. I'm going to do this by using some coordinates that you could get from your table in your calculator, but since the value of a is 1, I'm going to start by graphing 0, 1. Then go and multiply that by 3 each time, so 3 to the first power would be 3. 3 to the second power would be 9. So I've graphed 0, 1, 1, 3, 2, 9. We'll go into the negatives. 3 to the negative 1 power would be 1/3. Then I'd have 1/9, 1/27, and it would get closer and closer to the axis. I'm going to go ahead and graph this out right here. So for the function f of x, the domain is all real numbers, and the range is any number greater than 0. So I'm going to say f of x greater than 0, not equal to. Now I'm actually going to provide its inverse. Now you could do the inverse by actually reciprocating each point. And what I mean by that is that, I'm going to do this now in pink for the inverse. 0, 1 would become 1, 0. 1, 3 would become 3, 1. 2, 9 would become 9, 2. I think I graphed this previous one at 2, 10, so sorry about that. Okay, and I could also reciprocate these other values that were before 0. So negative 1, 1/3 would be 1/3 negative 1. And I'm swapping x and y for each one of these. You would see that the asymptote is now actually the y-axis instead for this function. The domain and range have also flipped. So now my domain for this new function is actually x, such that x has to be greater than 0. I don't have any x values that are negative for this pink function. All right, for my range is actually what's all real numbers now. And let's go ahead and actually write down what this inverse function would be. So if f of x was equal to 3 to the x power, I would invert that function by swapping x and f of x. And then I would solve for f inverse of x. A logarithm would be required here with a base of 3. So logarithm with a base of 3 of x equals logarithm base of 3 of 3 f inverse of x. On the right-hand side, it would cancel out. You'd be left with f inverse of x equals log base 3 of x. I'd actually flip that around so it's written more normally. F inverse of x equals log base 3 of x. So the logarithm here is the inverse of the original exponential function. This is how you do inverses for exponentials. We have to have this new operation of logarithm. You can see on our last example here, it's a word problem. They've represented Earth's atmosphere here on ground as being 1 atmosphere of pressure. And that's the reason why it's a 1 as our A value, which they didn't write. Times, you're losing 20% pressure for each mile you go up in altitude. That's the reason why it's 0.8. You're losing 20%. You're keeping 80% of your pressure. To the x power, where x is the altitude in miles. We're going to write an equation for the inverse function. Now, with inverse functions, we always swapped f of x and x. But in an application problem where you have defined your variables, really you don't want to go doing that, because if I swap x and p, all of a sudden p would be representing the wrong thing. So when it says write an inverse function, basically what it really means to do is just solve for the other variable. So I'm going to solve for the x on this current function. So p equals 0.8x. All I'd have to do is take a logarithm with a base of 0.8 on both sides. Because 0.8 was my base in my exponential. So the logarithm will have a base of 0.8 of p would equal x now on the right. This is my inverse function. Again, I don't go switching the variables on an application problem, because then that changes the meaning of the variables. What these are useful for, I'm going to say this, I would expect you to write down your notes. The original function is helpful for finding the amount of pressure at a given altitude. So if you know what altitude you're getting to, you'd be able to use this function to figure out your pressure. The inverse would do the flip of that. The inverse would tell you what altitude you need to get to in order to achieve a given pressure. Okay, so if you know what pressure you're wanting to achieve, this function, you'd plug it in right here, and x, when you evaluate it, would be what altitude you have to get to. All right, that wraps up the lesson. Do your homework and let me know what questions you got.